Cool. Thank you so much for having me. I'm really excited to talk to all of you today about the role of registries in developing rigorous standards for MRV of global enhanced rock weathering projects. So, for those of you who aren't familiar with Isometric and the work that we do, I'll just give a quick little rundown. Uh, Isometric is a carbon removal registry that was founded on the principles of scientific rigor, transparency, and collaboration. And our goal is to rebuild trust in the carbon markets. So, historical markets are uh, problematic in some ways and have been plagued by credibility concerns for a long time. And in order for long duration carbon removal to scale up to the orders of magnitude needed in order to achieve our climate goals and mitigate the worst impacts of anthropogenic climate change, we really need to have that trust because if buyers don't trust what they're buying, they're not going to buy. In order to bring this trust to the market, Isometric has a few solutions that we stand by. The first is, as I said, we're very focused on ensuring that our processes are scientifically rigorous. So we have a large team of in-house scientists, including myself, across various CDR pathways that write all of our protocols in-house, and we ensure that these protocols are up to date with the most current scientific consensus in each of those pathways. Secondly, we care a lot about aligned incentives. So we are paid by buyers rather than by suppliers, with our fee independent of the number of credits issued in order to align incentives and reduce conflicts of interest. So at no point will we ever exchange money with any of the suppliers whose credits that we verify. And we do this to avoid being incentivized to overcredit. And lastly, we're very passionate about transparency. So all of the data that underlies the credits that we issue is publicly viewable on our website. So anybody can go into our registry and redo those calculations themselves to ensure that everybody is appropriately accountable for the credits that are issued through the Isometric registry. What qualifies me to sit here and talk to you today about enhanced weathering protocols? The answer is I've written a lot of protocols, and one of them was co-authoring the Enhanced Weathering Protocol, which was first released in April 2024, and our most recent update was released in October of 2024. Spoiler alert, we are starting our initial planning stages of our next update. I can't give you any more details about that right now, but another update will be coming at some point next year. So, uh, I'm sure that we all know that enhanced weathering is great. I don't think I have to convince anybody here, and my fellow panelists have already talked about some of the amazing advantages of enhanced weathering, but I'll just go over them a little bit now as well. So, one reason that people get excited about enhanced weathering is that it is quite rapidly scalable because we are tying into a lot of existing infrastructure. So we already spread a lot of rock on farmland, so we don't have to go out and build a ton of new machines, build a ton of new plants in order to do enhanced weathering. And that's always going to be more inherently scalable because we can use what we already have. And of course, the things that I personally get the most excited about are things like co-benefits for agricultural efficiency. So as others have stated, we can see increased crop yields due to enhanced weathering. We can see increased soil nutrients, increased soil pH, decreased requirements for nitrogen fertilizers, potential for decreased nitrous oxide emissions, and we can also see some really important benefits for the local communities, such as job creation. So we love to see a CDR pathway that is good for the environment and good for the community. And I think enhanced weathering is something that really elegantly combines both of those things. But of course, nothing is perfect. So, as Rachel just very excellently explained, there are a lot of uncertainties associated with quantifying enhanced weathering. Our job as a registry is to figure out what we actually need to be thinking about when we quantify credits to go to market. To start off, I'm going to walk us through a little bit of how we consider this quantification within the isometric protocol. So this is the basic equation that we have in all of our protocols that essentially governs how we consider the calculation of a removal. So what we're concerned about is the net removal, which is the CO2e removal RP term. And for context, this E stands for equivalent. So this is CO2 equivalent. And this RP stands for reporting period, which is the period of time over which data is being submitted for a removal claim. So this is the net CDR that has happened within that reporting period, and that is equivalent to the CO2 that is stored. So in the case of enhanced weathering, that will be the CO2 that is drawn down as a result of the weathering process. And then we subtract out the counterfactual CO2 drawdown. So that is any CO2 drawdown that would have happened in the absence of project activities. So in the case of enhanced weathering, that can include any CDR that could have resulted from historical liming practice, or any CDR that could have happened from counterfactual weathering of the chosen feedstock. And then lastly, of course, we subtract out those project emissions because we want to make sure that the project is net negative, which means that their emissions cannot exceed the amount of CDR that is achieved through the project. So zooming in on this CO2 stored term, this is basically equivalent to the amount of CO2 that is drawn down, subtracted from the amount of CO2 that is then re-emitted to the atmosphere within that reporting period. So I'm going to go into a little bit more depth about both of those terms. So CO2 drawdown, as I said, is basically the amount of CO2 that is captured as a result of the rock weathering process. And this term incorporates a couple of things. So the most direct thing that is incorporated into this term is, of course, the soil and pore water sampling and analysis. So this is where we are actually quantifying the amount of feedstock that has weathered in our field at throughout the reporting period. There are also some other measurements that are important for understanding this term. So one of those is the feedstock CDR potential. And this is it basically if we lived in a perfect world where everything was perfectly efficient and 100% of the CDR that could have been achieved from the rock was achieved, how much is that CDR? So this is important because it basically sets an upper limit on the number of credits that we could possibly issue. So if we get data from a supplier that says that they have delivered CDR credits that are in excess of that theoretical potential, we know that something was wrong in the calculations or in some other aspect of carbon accounting, and it would be a major red flag for us to go and make sure that we evaluate all of that. And then the last important part that is not explicitly in this term, but is implicitly in this term, is these contextual measurements. So as we know, enhanced weathering is operating in an open system. And in order to have a robust quantification in an open system, we really need to understand what is happening at a system level, because we can't just measure what goes in and what goes out and expect that to be fully reflective of everything that has happened in between. So at this point in time where we are very reliant on direct measurements, and as Rachel said, there aren't that many catchment scale monitoring networks that are currently in place, understanding what is happening at that field scale can help us contextualize all of these other measurements that we are taking. So that can be things like soil pH, base saturation, things like that. So all of these different things that could be happening at the system level. So that is the drawdown term, and now I'm going to jump into the losses a little bit more. So as you can see, there are quite a few more terms that go into how we calculate the losses, but the main commonality that I want you to see behind all of these different terms is what we're really looking at are things that shift the charge balance of the system. So basically, what is taking alkalinity out of the system in a way that could cause any of that captured carbon to be re-released. So there are a couple of different ways that this can happen. One of them is through uptake of those cations by crops that are on the field. So that's that CO2e biomass term. Because again, we are removing those cations from the field, which causes a reequilibration to maintain charge balance. Secondly, we could have precipitation of secondary minerals, which could include carbonate minerals or silicate minerals, which also is removing alkalinity from the system. Rachel gave a great explanation of absorption and how that can be considered a loss. So that is considered a loss within the calculations in our protocol, and that is basically measured as changes in the base saturation. We can have interactions with strong acid, whether that is from fertilizer that's applied to the field, or if that is in the form of stored acidity that is absorbed to cation exchange sites on the soil particles. That can be a source of protons that can then interact with those dissolved bicarbonate ions and re-release that CO2 that has been captured into the atmosphere. And lastly, we think about downstream loss. So that is loss in the watershed, in rivers and oceans. And all of these, again, are really impacting the charge balance. So that could uh, results in those bicarbonate ions being respeciated to CO2 and then released to the atmosphere. And these things are all quantified by some combination of in-field measurements and farmer supply data, most commonly. And then in the case of downstream losses, we do allow for site-specific empirically validated models for quantification using those. So one of the things that we think a lot about is what is the best way to measure each of these things and what is the best way to quantify each of these things. And then after we've thought about the best way, we ask ourselves, is that the most cost-effective way? Are there other ways that could provide a similar result that could cost less? And ultimately, in our role as the registry, we don't tend to actually mandate exactly what measurements need to be taken, only what needs to be quantified. And we work very closely with suppliers like InPlanet to make sure that all of these things are quantified in a way that follows the guidelines of our protocol. And this is something that we are always looking to iterate on and improve on. Um, and the reason that we think a lot about this is because uh, we are often thinking about how things can vary from different project locations. So, enhanced weathering projects take place all over the world. Of course, we have amazing suppliers like InPlanet that are operating in Brazil. We have several suppliers operating in the US, several suppliers across Europe, across India, and other parts of Asia, across Africa. So, there are lots of different projects, which means that there is a lot of diversity in the environments that those projects are taking place in. And because of these benefits that enhanced weathering can have, especially in communities that are historically plagued by poor soil health, particularly in rural communities where there can be additional job creation. We really want these social benefits to be able to impact those communities as well. So the last thing that we want to do is write a protocol that nobody can use, because if nobody can achieve the requirements of the protocol, then CDR doesn't happen. We don't get any of these benefits for the climate or for the community. And that's not the outcome that we want. So we spend a lot of time talking to suppliers about different things that are impacting their operations that could impact how we view the proper way for things to be quantified. So the reason I've thrown this image up here is because we heard a lot from Rachel about heterogeneity in the field, and we think a lot about how that can properly be quantified, but I think it's also really important to think about variability between different environments where enhanced weathering projects can take place and how variability in those environments can impact how we think about measurements. So, for instance, in this diagram, we have things represented like soil texture. That's what these little three dots are. That's supposed to represent soil texture. We have different microbial communities. We can have different crop types. We, of course, have the impact of different climatic zones. We can have differences in topography that can have an impact on how water is transported in the system. Of course, there's different availability of feedstock. So these are all things that we keep in mind when we are writing a protocol to make sure that it can actually be operable worldwide. And I want to talk a little bit more about types of things that we consider when we're making sure that a protocol can actually be applied globally. And this is a little segment I like to call Things Happen Everywhere. So some things that happen in every project is you have different impacts of farm management. So different areas can have different crop types and different crop rotations. Tillage is more common in some areas than others. And the type of tillage matters when you're thinking about how you should sample for quantifying enhanced rock weathering. Different types of fields require different additives. So you can have different types of fertilizers. You can have different historic liming practices or fertilizer addition practices. Suppliers always have to think about planting and harvest time and schedules when they're thinking about when you deploy. And that, of course, has implications both in terms of project management for the supplier, timelines for credit delivery, and the overall timelines for weathering. Because if you're deploying during the rainy season, that's going to look a lot different than if you're deploying during the dry season. That's probably not a great example, but it's the first one that came to mind. And then secondly, data processing. There are actually a lot of differences in how data is processed depending on where you are, primarily because of things like proximity to lab facilities. So if you're right next to a high quality lab that lets you use their facilities, that looks a lot different from a project perspective than if you have to ship something either on the road or through or using a plane. So proximity to lab facilities and ability to use those lab facilities is different depending on where you are. Similarly, the ability to maintain a cold chain is something that I've actually spent a lot of time thinking about and how that can impact the ability to process data. So, for different types of samples, it's really important that they are stored in a cold place for that measurement to be reliable. And depending on where you are in the world, that actually might not be a super easy thing to do. So we've talked with several suppliers about how we can help enable them to make sure that they're still getting high quality measurements when they don't necessarily have access to a lot of these resources. And similarly, access to materials and equipment looks different in different places. In some places, it can be really easy. In some places, it can be really hard. And we want to make sure that we are being sensitive to those concerns and considerations. And then lastly, of course, we have different concerns with operations. So topography is something that I mentioned earlier that can potentially impact the way we quantify weathering because of the different flow paths for water, but it can also impact sampling, for example. It's a lot easier to sample on a flat plane than it is to sample on the side of a mountain. So if you are operating in different regions with different topography, that's something that we need to make sure that we can accommodate with our methodology. And similarly, differences in climate. I just gave the example of the rainy season versus the dry season. It's a lot harder to have a good and regular pore water sampling cadence if you're operating somewhere with a monsoonal climate where you have a huge amount of rainfall. As Rachel mentioned in the last talk, you can have huge amounts of flux through that system. That means it's really difficult to actually sample to make sure you're getting a full picture because of the high water flux. And one fun anecdote that I always think of with InPlanet is that sometimes there can be snakes in your project area or other sorts of dangerous fauna. So you need to make sure that your staff is safe and that the people that you're sending out to the field are adequately protected. So there's a lot of different things, as you can see, that we have to think about both from the actual quantification perspective, which I think was really well summarized by Rachel in terms of all the things that we need to think about, and then also just in terms of operations and things like relationship with your agricultural partners, how you're going to get samples to where they need to go, how you're going to make sure that your staff is adequately supported, and all of those different types of things. So to wrap up, I want to summarize how we are thinking about making sure that our protocols are globally operable. And for enhanced weathering specifically, I think there are three key principles that I always come back to. So the first is flexibility. So we talked a lot about how regional variations in topography and climate and analytical availability can impact how we think about MRV. And this really necessitates a project-based approach at this point in time in the field. I do think that as we have more enhanced weathering deployments and we have more data from a huge diversity of different projects, we might start to see more similarities and see more ways that we can apply learnings from one area to another area, but we're not quite there yet. So at this point in time, maintaining that flexibility is really important to make sure that we can incentivize all of these projects around the world. Secondly, sensitivity is really important because, of course, we always want to be making sure that we are prioritizing the safety and privacy of agricultural partners while also maintaining that balance with data transparency that is so critical to get enhanced weathering to scale. So we want to make sure that all of that private data is protected while making sure that we can still publicly display the data that matters for knowing how enhanced weathering is quantified. And then lastly, specificity is still really important and needs to be balanced with flexibility such that when we generate a credit from Brazil, that is the same as a credit that is generated in the US, same as a credit that is generated in Germany, same as a credit that is generated in India. All of these credits need to be functionally the same, and we need to have enough specificity in the protocol to make sure that that can happen. So making sure that we balance those two things is a really, really high priority for us at Isometric when we're working on these protocols. And it's a fine tightrope to walk, but definitely something that is achievable, particularly in partnership with project developers who have been so open and welcoming to talk to us about their different processes. And we can make sure that these different things are incorporated when we're thinking about protocol development. So that is, I think, all of my slides to talk about. So I'll throw this up on the screen. This will take you directly to the Enhanced Weathering Protocol on the Isometric Registry if you are interested in reading it. And I'm happy to take questions if we have time.
Thanks, Ella, for the presentation. And to be honest, I think as in planning, we're really enjoying the collaboration with Isometric. So I think we do have some questions here. The first one we have is that there's have been one credit issuance happening in Brazil, and the audience was wondering whether there's any goal in terms of certification for the coming years.
Yes, so I obviously can't name names or say where they are happening, but we do have several verifications in the pipeline. We definitely expect to issue more credits in the short term.
Okay, great. Sounds good. And the next question would be, so the audience asks how the protocols and calculations from Isometric are validated by who?
Sure. So th this is primarily for the validation and verification body, or VVB. So this is an external third-party verifier that Isometric contracts with to support on the verification. So the VVB will do things like go to the site where the project is happening to make sure that everything that they have listed in their project design document is actually happening at the field level. And then Isometric is involved in this process in that we review the project design document. We work closely with the supplier to ensure that the project is in compliance with our protocol. We carefully review all of the different calculations that the project developer has done, but the final verification and sign off on the credit issuance comes from that third party verifier because, again, we don't want to be the ones marking our own homework. So we are involved in the process, but the final approval comes from the verifier.
Okay, great. And then the next question is about whether there's any limitations on interlab variation of data.
That's a great question, and something that I don't think is super well constrained right now. I know that Noah Planatsky at Yale and several other academics are currently working on collaboration. I believe Anu Khan is also working on that collaboration to get a comparison of data from these different labs.
Okay, great. So I think these are the questions from the audience, but I also have a question from myself. So I was wondering, so as isometric, of course, we want to keep the highest level of scientific rigor, but I was wondering from the isometric point of view, how you balance scientific rigor, scalability, and feasibility of different projects.
Yeah, that is a fantastic question and one that we grapple with very often. So I think that the way that a super open way to say this is that we are very open-minded. So we tend to start off from one point, and as we gather new information, never uh, we we never say like, because we wrote it this way, it has to be this way forever. The protocol that we first released is extremely different than the protocol that we have now because we're always incorporating learnings that we get from doing the verifications and talking to more suppliers and more academics into the protocol. So the most recent update that we released last October was in large part motivated from the learnings from the first InPlanet verification, where we learned a lot about the realities of how we actually quantify heterogeneity in the soil. Previously, the original version of the protocol had a mandatory sampling minimum, and after working on the verification of the InPlanet credits, we realized that the number of samples that you need to fully quantify the variance is pretty specific to the field. So that's an example of something that we made more flexible after realizing that having a strict minimum was both operationally difficult and not actually adding any rigor. So it's a lot of that, of making sure that we are constantly reassessing and reevaluating the assumptions that we've made and making sure that they are actually there to improve the quality of the credits that are issued at the end and not just there because of an arbitrary decision that we made in order to make sure that we were doing something, basically. Mhm.
Great, thanks. So
Mhm.
we have one more question from the audience. It's a more specific question. So they were wondering what kind of tasks need to be done for the feedstock before we can safely deploy it to the field.
Yes, so we actually have a rock and mineral feedstock characterization module that uh, we use for all the requirements for feedstock monitoring. Basically, what we need to know is what is the composition of the feedstock, both in terms of mineralogy and in terms of the elemental composition. So for mineralogy, we want to know if there's any things like asbestos in there that could potentially contaminate the field, as well as get an idea of what the expected weathering rate is. For the elemental composition, we use that to calculate the CDR potential of that feedstock, and we also use that to evaluate the potential for heavy metal contamination. And then we need to know some physical parameters of the feedstock, like the surface area, the particle size distribution, and that is partially for understanding, again, the weathering rates of that feedstock, and also partially to understand if there are any physical hazards that need to be accounted for in any environmental and social safeguards.